There is a light on somewhere in your house right now. Perhaps you left it burning in the kitchen before you came to sit here. Perhaps it's in a hallway or a bathroom, left on by habit or necessity. That single light, in an otherwise dark house, creates something we rarely stop to consider. It creates structure in the darkness. It makes one region of space fundamentally different from another. Here there is light, there is not. This is what we assume about the universe. We assume that the cosmos, in its earliest moments, was not entirely uniform. We assume that somewhere, somehow, there were places where matter gathered just slightly more densely than in other places. Tiny imperfections, microscopic differences. And we assume that these small differences over billions of years grew into the galaxies we see scattered across the night sky like lights left on in an otherwise empty house. It seems reasonable. It feels intuitive. After all, we see galaxies. They exist. They must have come from somewhere, grown from something. The assumption is that the universe began in a state of near perfect smoothness, and that gravity, working patiently across cosmic time, amplified tiny irregularities into the magnificent spiral and elliptical structures we observe today. This assumption is so deeply embedded in modern cosmology that we barely recognize it as an assumption at all. We speak of galaxy formation as though it were a solved problem, a chapter closed in the textbook of cosmic history. We have computer simulations that show dark matter clumping together. We have theories about how gas cooled and collapsed. We have observed distant galaxies, their light traveling to us across billions of light years, offering glimpses of cosmic adolescence. But here is what we forget. When we speak with such confidence, we have never seen a galaxy form. We have only ever seen galaxies that have already formed, frozen in whatever state they happened to be when their light began its long journey toward us. We are looking at photographs of lights that were turned on billions of years ago, trying to understand how the switch was flipped. That single light in your house, the one you left burning, required something before it could illuminate the darkness. It required wiring, a circuit, a connection to a source of power. It required someone to flip a switch. The light did not simply emerge from the darkness spontaneously. There was a mechanism, there was a sequence of events. What was the mechanism that first turned on the lights in the universe? The deeper we look into the early universe, the more troubling our assumptions become. We can observe galaxies as they appeared when the universe was very young. Not as young as we once thought possible, but young nonetheless. Telescopes like the James Webb Space Telescope have pushed our vision back to times when the cosmos was only a few 100 million years old, less than 5% of its current age. And what we see there is unexpected. We see galaxies that should not exist yet. These early galaxies are too large, too structured, too mature. They contain too many stars. They have formed too quickly. According to our models of how gravity works, according to our understanding of how matter clumps together, these galaxies should still be formless clouds of gas, still gathering themselves, still preparing for the long, slow process of galaxy formation. But they are already galaxies. The lights are already on. This creates a fundamental problem. Our assumption was that galaxy formation was a gradual process, that the tiny imperfections in the early universe would take time to grow, that gravity would need billions of years to pull matter into the dense, organized structures we call galaxies. But if galaxies were already well formed when the universe was a child, then either gravity worked faster than we understand, or the initial imperfections were not as small as we assumed, or something else entirely was happening that we have not yet recognized. There is another problem, subtler but perhaps more profound. When we observe the early universe, we are not actually observing the early universe. We are observing light that left the early universe billions of years ago. We are seeing ancient photons that have been traveling through expanding space for most of cosmic history. These photons have been stretched by the expansion of the universe, their wavelengths lengthened, their information distorted. We must reconstruct what we think we are seeing, extrapolating backward through cosmic time, correcting for expansion, accounting for all the ways that light can be altered on its long journey. We are not witnessing galaxy formation. We are interpreting clues left behind by galaxy formation, and interpretation always requires assumptions. What if the assumptions we use to interpret these ancient signals are themselves based on incomplete physics? What if the universe in its infancy operated according to principles we have not yet discovered? We are using the physics we understand today, physics that describes the universe as it is now, to explain the universe as it was then. But the early universe was not like the universe today. It was hotter, denser, more energetic. It was a place where quantum effects might have operated on cosmic scales, where forces we consider distinct today might have been unified. We assume that the laws of physics were the same then as they are now. We assume this because we must. Without this assumption, we have no way to interpret what we see. But an assumption made out of necessity is not the same as an assumption made from certainty. How can we be sure that the universe has always operated according to the rules we observe today? There is a moment in the history of the universe where our physics simply stops working. We call it the Planck epoch, the first tiny fraction of a second after the beginning, when the universe was so hot and so dense that all our theories break down. Quantum mechanics and general relativity, the two great frameworks of modern physics, give contradictory answers about what should happen under such extreme conditions. We have no unified theory that describes this moment. We have mathematics, but the mathematics produces infinities, nonsensical results, predictions that cannot be tested. We skip over this moment. We begin our story of the universe a fraction of a second later, when the physics becomes tractable again, when our equations start producing meaningful predictions. But that skipped moment is where everything began. That is when the imperfections we rely on must have been created. That is when the seeds of all future galaxies were planted. We are trying to understand how galaxies formed by starting our story after the most important part has already happened. Consider what we know must have occurred. The early universe, according to our best observations, was remarkably smooth. When we observe the cosmic microwave background, the afterglow of the Big Bang, we see temperature variations of only 1 part in 100,000. This is the snapshot of the universe when it was just 380,000 years old. It was almost perfectly uniform. Almost, but not quite. Those tiny variations, those small regions that were just slightly denser or slightly less dense than average, are what we believe led to galaxy formation. Gravity, we say, amplified these differences. Where matter was slightly more concentrated, gravity pulled in more matter. This made the region denser still, which made its gravity stronger, which pulled in even more matter. A feedback loop, a snowball effect. Over hundreds of millions of years, these small overdensities grew into the first stars, the first clusters, the first galaxies. This is the standard picture. But it raises immediate questions. How small of a difference is actually required? If the variations were too small, gravity would not have enough time to amplify them before the expansion of the universe pulled everything apart. If the variations were too large, everything would have collapsed into black holes almost immediately, before stars could form, before galaxies could take shape. The initial conditions had to be tuned precisely. Not perfectly smooth, but not too lumpy either, just rough enough. Why was the early universe tuned this way? We do not know. We call it initial conditions and move on. And then there is dark matter, the invisible substance that apparently makes up most of the matter in the universe. We invented dark matter to solve a different problem, to explain why galaxies rotate the way they do, why galaxy clusters are held together more strongly than visible matter alone could account for. But dark matter has become essential to our story of galaxy formation. In our simulations, dark matter clumps together first, forming gravitational scaffolding that ordinary matter can then fall into. Without dark matter, the ordinary matter we can see would take far too long to clump together. The galaxies would form too slowly. But we have never detected dark matter directly. We infer its existence from gravitational effects. We assume it exists because without it, galaxy formation as we understand it becomes impossible. The assumption of dark matter is necessary to preserve the assumption that galaxies formed gradually through gravity. What if both assumptions are wrong? The first stars changed everything. When they formed inside the first dark matter halos, when they ignited nuclear fusion in their cores, they were not like the stars we see today. They were massive, hundreds of times the mass of our sun. They burned hot and fast, and when they died violently, in supernova explosions that blasted heavy elements into space, that heated the surrounding gas, that created bubbles of energy expanding outward at tremendous speeds. These first stars reionized the universe. They turned neutral hydrogen gas back into a plasma. They made the universe transparent in new ways, allowing light to travel freely. But they also made the universe more chaotic. They injected energy into the gas that was trying to collapse into galaxies. They made gravity's job harder. And yet galaxies formed anyway. Somehow, despite this violence, despite this disruption, structures persisted. The light stayed on. We can see these early galaxies now, or at least we see their ancient light. And they are not quite what we expected. They are smaller than the galaxies we see today, but they are also denser, more compact. Their stars are forming at prodigious rates. They are turbulent, clumpy, irregular. They do not yet have the elegant spiral arms or smooth elliptical shapes of mature galaxies. They are raw, unfinished. What do these shapes tell us about how they formed? What do their motions reveal about the forces that sculpted them? We study them by analyzing their light. We break their light into spectra, measuring which wavelengths are present and which are absent. This tells us what elements are in their stars, how fast they are moving, how hot they are. We measure their sizes, their masses, their rates of star formation. We build up statistical pictures of what the early universe looked like, how common different types of galaxies were, how they changed over time. But we cannot watch them evolve. We see each galaxy frozen at one moment in its history. We are looking at billions of different galaxies at billions of different stages of development, trying to piece together a single coherent story. We are looking at billions of photographs of different lights in different houses, trying to understand the nature of electricity. The problem is that we are reconstructing events we can never directly witness. Galaxy formation happened once, in each location, billions of years ago. We cannot rewind time. We cannot run experiments. We can only observe the aftermath and try to work backward. And the further back we look, the more uncertain our reconstructions become. There are scientists who believe that the first galaxies formed from the bottom up. Small structures first, then larger structures built from smaller ones. Tiny dark matter halos formed first, then merged together into larger halos. Small clumps of stars formed first, then assembled into galaxies. This is the hierarchical model, and it is supported by our understanding of how gravity works, how structures grow in an expanding universe. But there are also scientists who point to evidence for the opposite, who see signs that some of the first galaxies formed from the top down, that massive structures formed first and then fragmented into smaller pieces, that the first galaxies were actually quite large, and that smaller galaxies we see today are the debris, the leftovers, the fragments of something grander that existed in the beginning. The data does not clearly favor one picture over the other. Different observations can be interpreted in different ways. A galaxy that appears massive might actually be several smaller galaxies in the process of merging. A galaxy that appears small might be only the bright center of a larger structure whose outer regions are too faint to detect. We are limited by what our telescopes can see, by how sensitive our instruments are, by how much time we can spend staring at tiny patches of sky. There are models that involve cold dark matter, the most popular framework, in which dark matter particles move slowly and clump together through gravity alone. But there are also models involving warm dark matter, where the particles move faster, and this motion smooths out small-scale structure. There are models with self-interacting dark matter that can collide with itself. There are models where dark matter does not exist at all, where gravity itself behaves differently on large scales than we understand. Each framework predicts different patterns for how galaxies should form. Each makes different predictions about what the first galaxies should look like. And each framework can be adjusted, tuned, modified to match observations. We add new physics, new processes, new parameters. We make the models more complex until they agree with what we see. But complexity is not the same as understanding. Some researchers argue that the first galaxies formed in special places, in the densest regions of the early universe where gravity was strongest. These would have become the cores of galaxy clusters, the most massive structures we see today. Other galaxies formed later, in less dense regions, building up slowly over billions of years. Others suggest that feedback processes were more important than we recognize, that supernova explosions and black hole accretion created powerful winds that blew gas out of small galaxies, preventing them from forming stars, stunting their growth. That only galaxies above a certain mass threshold could retain their gas and continue forming stars. That the smallest galaxies we see today are survivors, the ones that somehow manage to hold on to their gas despite these disruptive forces. There are theories about cosmic web formation, about how matter arranged itself into filaments and sheets with vast voids in between. Galaxies formed along these filaments where matter was concentrated, where gravity was most effective. The large-scale structure of the universe guided where galaxies could form. And there are theories about primordial black holes, about massive black holes that existed before the first stars, that could have seeded the formation of the first galaxies by providing powerful gravitational anchors. We have found supermassive black holes in the centers of very distant galaxies, black holes that seem too massive to have grown from stellar remnants in the time available. Where did these black holes come from? How did they get so massive so quickly? We do not know. We have competing hypotheses, each with strengths and weaknesses, each capable of explaining some observations while struggling with others. This is the nature of frontier science. We have not yet converged on a single unified picture. We are still exploring the possibility space, still testing ideas, still accumulating data. The story is not finished. Perhaps it will never be finished. If galaxies did not form the way we think they formed, if the assumptions underlying our entire cosmological framework are incorrect, then we are misunderstanding something fundamental about the nature of the universe itself. Consider what we have built upon these assumptions. Our entire picture of cosmic history depends on galaxy formation happening when and how we think it happened. We have constructed a timeline of the universe, a narrative that begins with the Big Bang and proceeds through a series of epochs: first light, first stars, first galaxies, galaxy mergers, galaxy clusters, the universe we inhabit today. Each stage builds on the previous one. Each stage assumes that gravity, dark matter, and the expansion of the universe operate according to our current understanding. If the first galaxies formed too quickly, if they were too massive, too structured when they should have been chaotic and incomplete, then perhaps dark matter behaves differently than we assume. Perhaps it interacts with itself or with ordinary matter in ways we have not detected. Perhaps there are forces we have not accounted for. pressures, or fields that influenced galaxy formation, but left no trace we can recognize. Or perhaps the early universe had different initial conditions than we extrapolate from our observations. Perhaps the imperfections were larger, more organized, more structured than the cosmic microwave background suggests. Perhaps there was physics operating in that first moment, that Planck epoch we cannot describe, that created patterns we have not yet recognized. If this is true, then our understanding of the Big Bang itself might be incomplete. We might be missing crucial details about how the universe began, what caused it to expand, what determined its initial state. The story we tell about the origin of everything might be wrong in ways we have not yet imagined. There is also a more philosophical implication. We assume that the universe is comprehensible, that we can understand its history by observing its present state and applying physical laws backward in time. We assume that the processes we see operating today are the same processes that operated in the past. We assume continuity, consistency, that nature follows rules we can discover. But what if galaxy formation was a unique event, something that happened under conditions so different from anything we can study today that our entire framework of understanding is inadequate? What if the early universe was not just hotter and denser, but fundamentally different in ways that matter, in ways that break the assumptions underlying our physical theories? Then we would be in the position of someone trying to understand how a light works without ever having access to electricity, without being able to take apart a bulb or trace the wiring. We would be confined to observing the light itself, its brightness and color, and trying to infer from these observations alone the entire infrastructure that makes illumination possible. We would be guessing, however educated our guesses might be. And if we cannot reliably understand the first galaxies, if our reconstructions of the early universe are built on unstable foundations, then what does this say about all the other conclusions we have drawn? What does it say about dark energy, the mysterious force causing the universe's expansion to accelerate? What does it say about the fate of the cosmos, whether it will expand forever or eventually collapse? What does it say about the possibility of other universes, other regions of space with different physical laws? All of these ideas depend on our cosmological models being approximately correct. They assume we have the basic story right, even if details remain to be worked out. But if the basic story is wrong, if galaxy formation did not proceed the way we think it did, then we are building castles on sand. We are constructing elaborate theories on foundations that might not support them. This is not a comfortable position for science to be in. We prefer certainty, or at least confidence. We prefer to know which questions are answered and which remain open. But the universe does not care about our preferences. It does not arrange itself for our convenience. Perhaps the most honest thing we can say is that we do not know how the first galaxies formed. We have ideas, frameworks, simulations. We have observations that constrain some possibilities while leaving others open. But we do not know. Not yet. Perhaps not ever. There is still a light on somewhere in your house. It is still creating structure in the darkness, still making one region fundamentally different from another. And you still do not think about it, because light is so familiar, so ordinary, so completely integrated into your daily experience that you forget it requires explanation. Galaxies are the lights of the universe. They are the structures that break the monotony of empty space, that create regions of density and activity in a cosmos that would otherwise be formless. And like that light in your house, they seem so ordinary now that we forget how extraordinary their existence actually is. We began with an assumption that small imperfections in the early universe grew, through the patient work of gravity, into the galaxies we see today. This assumption has guided decades of research, inspired countless simulations, shaped our entire understanding of cosmic history. But the more we look, the more we find that the assumption is strained. The first galaxies appear too early, too well formed. They challenge our expectations. They suggest that something we think we understand is not quite right, that some piece of the puzzle is missing or misplaced. What was the mechanism that turned on the lights in the universe? We have proposed answers: dark matter halos, gas cooling and collapsing, the first stars exploding and enriching space with heavy elements. We have traced out possible pathways from uniformity to structure, from smoothness to the complex architecture of galaxies. But we have not witnessed these pathways. We have inferred them, reconstructed them, simulated them. We have never seen a galaxy form. We have only ever seen galaxies that have already formed, their light traveling to us across unimaginable distances, carrying information that we must painstakingly decode. And in that decoding, we make assumptions. We assume the light has not been altered in ways we cannot detect. We assume the laws of physics that describe the universe today also describe the universe then. We assume our instruments are telling us what we think they are telling us. We assume because we must, because without assumptions we cannot proceed, because science requires some foundation to build upon. But foundations can be questioned. Assumptions can be tested, challenged, revised. Perhaps galaxy formation was faster than we think. Perhaps it was slower. Perhaps it was more chaotic or more orderly. Perhaps dark matter is not what we imagine it to be. Perhaps gravity itself, in the extreme conditions of the early universe, operated differently than it does today. Perhaps there are entirely new forces, new fields, new physics operating on scales we have not yet learned to observe. We do not know. This is not a failure of science. It is the nature of science. We probe the unknown with the tools we have. We build models that fit our observations, and then we find new observations that challenge those models. We revise, refine, occasionally overturn everything we thought we knew. The first galaxies are still out there, or rather, the light from the first galaxies is still reaching us, still carrying information from the cosmic dawn. We are building better telescopes, developing new techniques, gathering more data. We are slowly assembling a more complete picture of what the early universe looked like. But we may never have a complete picture. We may always be limited to glimpses, snapshots, fragments of the full story. We may always be in the position of someone examining a single light bulb, trying to understand the entire electrical grid. And perhaps that is acceptable. Perhaps it is even profound. Perhaps what we learn about the universe is not just what it is, but how much we can learn about it, and how much will always remain beyond our reach. You will turn off that light eventually, the one you left burning in your house. The room will return to darkness, but even in darkness, the structure remains. The walls, the furniture, the architecture that the light revealed, all of it persists whether illuminated or not. The first galaxies formed in the darkness of the early universe, turning on the lights for the first time in cosmic history. How they did this, why they did this, when and where they did, remains one of the deepest questions we can ask about the nature of existence. We have our theories, our simulations, our observations. We have our assumptions. But assumptions are not answers. They are starting points, temporary placeholders for the understanding we hope to achieve. The lights are on. They have been on for billions of years, and we are still learning how to ask the right questions about them.